This is our second lesson here in Unit 15. We're covering boxes C and D, and we're looking at a specific kind of optimization problem. We're going to be looking at optimizing costs here. So let's just take a look at a couple of examples here. The first example, we got a city here setting up community garden plots for residents living in apartments. The plots are going to be arranged as shown in this little diagram here. So we've got 5 of them along one side and 4 of them down another side. And each plot will be 24 meters squared. We're going to have fencing in between the plots and then around the outside of the perimeter of the entire garden. Now here's where the cost part comes in. The fencing between the lots costs $4 per meter, and the fencing around the entire area, around the outside of the perimeter, costs $8 per meter. What should the dimensions of the plots be, that's each individual plot, to minimize the cost of fencing that we have to buy here? Now, first thing we're going to need to do here is, obviously, since this is an optimizing cost question, we are looking to optimize or minimize the cost of fencing. What we need to come up with is a function that represents the cost of fencing that we're going to have to buy. And before we can do that, we need to pick some variables in this question. So because we're asked for the dimensions of the plots themselves, it makes sense to choose variables that represent the dimensions of the plots. So we'll say let L be the length of one plot, and we can let width be the width of one plot. Okay. Now, what do we know about length and width right off the top? Do we have a relationship between length and width? They give us the area of each plot. So we know that that has to be 24, and that 24 has to be length times width. So we're going to use that piece of information at some point. But now we have to work on figuring out how much this fencing is going to cost. Okay? We want a function that represents the cost of the fencing. Before we can get that function, we need to know how much fencing we are going to need. So let's just say we got fencing here. Okay. And we have 2 types of fences, 2 types of fencing. We've got the stuff around the outside, and we have the stuff in the middle. So let's consider these 2 things separately. How much around the outside, and how much, we'll say, inside or in between. So if we come to our little diagram over here, we'll say that our length is over here, and our width is like that. So one little plot, we've got the length going horizontally and the width going vertically. If we want to go around the outside, we can just count up how many of these little widths or little W's we need to go around the outside. We need 1, 2, 3, 4, 5, 6, 7, 8 widths. And then to do our 2 horizontal sides here, we need 1, 2, 3, 4, 5 lengths, and then another 5 on top. So we need 10L meters of fencing to go around the outside. Now, how much do we need on the inside? Well, let's see. If we count widths again, we need 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So we need 16 widths. Those widths, remember, are vertical. And then if we look at the horizontal sections just on the inside, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we need 15 of those length sections. So this is the amount of fencing that we are going to need in terms of W and L. We can use this to get our cost function. Okay? How much does the fencing around the outside cost? Well, the outside stuff costs $8 per meter. So we'll have 8 times the amount of fencing that we need. 8W plus 10L. Stuff on the inside costs $4. So we're going to have 4 times 16W plus 15L. And I'll just add in this stuff over here is, this is our $8 per meter, and this over here is our $4 per meter. So now we have our cost function. Let's simplify this a little bit. So 64W plus 80L plus, let's see, 4 times 16 is 64W plus 60L. And let's collect our like terms here. 64 and 64 gives us 128 widths. 80 plus 60 gives us 140 L. And instead of cost, I'll just write C here and C here. Okay. So this is the function that tells us how much this is going to cost. This is what we want to optimize. So we're going to want to take the derivative, set it equal to 0, and solve for our critical numbers. Something we have to do before that, though. What is it? What do you think, Richard? What do we have to do first? We can't find our width and length. That's going to come right at the very end. What's the problem with taking the derivative of this thing? It's just numbers. Well, it's got variables in there. Width and length are our variables here. So we're going to take the derivative of this with respect to one of our variables. But wait. Nope. There's 2 variables. We want 1 variable so we can differentiate this. So we use our relationship between length and width and the area that we got up here. So what I am going to do is I'm going to take this relationship and I'm going to figure out what my width is in terms of my length. Let's see, divide through by L, 24 divided by L. Now I'm going to plug this down into my cost function to get a function of 1 variable. So width is 24 divided by L. And there is the cost function that I can hopefully take the derivative of. So let's just rewrite this in a form that is a little easier to take the derivative of. The 128 times 24 works out to 3072. Change my 1 over L there to an L to the negative 1. And add in 140L. Okay. Let's take our derivative. What's my derivative going to be here? How do I differentiate this thing? Nick. All right. Okay. So I got my derivative. I'm looking for a max or minimum. Well, I'm looking for a minimum. So I want to set this equal to 0 and solve for L. So I'm going to keep the 140 on this side. I'm going to bring this first term here over to the other side, and I'm going to get 3072 over L squared. And just rearranging this. And that's going to get me L squared is 3072 over 140, or L is the square root of 3072 divided by 140. So this is going to give us the length here. So our length, we work this out, I think we get 4.68. Okay. What else do we need to do here? Find the width. Even before we find the width, what's something else we should do? Remember, we're looking for the minimum cost here. We should verify that this length gives us a minimum rather than a maximum. How do we do that? Right. So our second derivative is going to be, let's see what we got here. We got to bring down this -2, so that's going to give us 2 times 3072 L to the -3. And I want to evaluate this at our value of length here. So if I sub in 4.68, I'm going to have 2 times 3,072. Now, I don't know what 2 times 3,072 is. I don't actually care at this point because I'm really not interested in the value here. I'm interested in whether this is positive or negative. So I know the numerator is going to be positive. When I sub in 4.68 cubed, I can look down at the denominator there and I see, well, I've got a positive number cubed, so this is going to be positive. So this whole thing is going to be greater than 0. And if my second derivative is greater than 0, does that tell me I have a maximum or a minimum? Let's see. Positive, positive, happy face. I've got a minimum. Okay. So this does, in fact, correspond to a local minimum. Now I just need my width. So how am I going to get my width? Yeah. So I've got my width is 24 divided by my length, 4.68. And I can work that out and get, I get 5.13. And so we are done here. Therefore, let's just say each plot should be .13 meters by 4.68 meters. And we're done.